Hi everyone and welcome. In today's tutorial, you will learn how to make the QNLI dataset, fine-tune a DistilBERT model step by step from scratch using the Hugging Face transformers model. Here is what we will cover. Number 1. Setting up a Python virtual environment and installing what you need. Number 2. Loading and exploring QNLI with Hugging Face datasets and PyTorch Dataset. Number 3. Tokenizing and encoding question sentence pairs. Number 4. Building a simple PyTorch dataset class. Number 5. Initializing the model and trainer. Number 6. Training the model. Number 7. And lastly, evaluating, saving your model and using it for predictions. So let's dive in. QNLI stands for Question Natural Language Inference. You give the model a question and a candidate sentence. It predicts whether the sentence answers the question, entailment or not entailment. Let's take a closer look at the QNLI dataset. QNLI is one of the tasks in the GLUE benchmark designed to provide a collection of resources for training, evaluating, and analyzing natural language understanding systems. QNLI itself was derived from the Stanford Question Answering Dataset, also known as SQUAD, but reformulated as a sentence pair classification task. The full QNLI set contains roughly around 116,000 records. Across all splits, it uses roughly around 40 MB of storage. Each example looks like this in JSON. Before we dive into the code, here's QNLI through the FAIR principles. It's findable since it's available on GLUE, Papers with Code, and Hugging Face Hub with stable URIs and metadata. It is accessible since you can download it from GLUE or Hugging Face. It is interoperable since its plain JSON format fits any NLP pipeline. And it's reusable since it's open for extension. So what is Hugging Face? Hugging Face is an open source community that maintains the transformers and dataset libraries, giving you instant access to hundreds of pre-trained language models, tokenizers, and data pipelines. We're using it here because it makes loading QNLI, tokenizing text, initializing models like DistilBERT, and running training or evaluation as simple as writing few clear lines of code. Let's begin our setup. First, let's isolate our work in a Python virtual environment. A virtual environment keeps your project's libraries isolated from other Python projects. It prevents version conflicts. For example, you might need Transformers 4.x here, but another project needs 3.x. Lastly, it makes it easy to reproduce your exact setup later or share with collaborators. We will be setting up and using the following libraries. You can simply install them using pip. Now you can import these libraries in your Python code. We will be using the Hugging Face dataset library to download and load the QNLI data. GLUE specifies the GLUE benchmark collection, and QNLI picks the Question Natural Language Inference portion of GLUE. You'll see 4 columns: question, sentence, which may or may not contain the answer to the question, label, entailment or not, and IDX, which is the ID of the record. Next, we turn each split of the row QNLI dataset into a pandas data frame, which makes it easy to inspect and manipulate. Training set is the largest portion of the data. We use it to fit the model, that means to learn the weights. Validation set is a separate slice held out from training. We use it to tune hyperparameters, monitor for overfitting during training, and decide when to stop. Test set is the final holdout data that the model never sees during training or validation. After you're fully done, you run your model on this set to get an unbiased estimate of real-world performance and to generate predictions for new dataset. The results will be similar to what I showed earlier, just with a split. Next up is tokenization and encoding. Tokenization is how we break raw text into smaller pieces or tokens that the model understands. For BERT-style models, tokens are often subwords. After tokenization, each token is mapped into a unique integer ID from the model's vocabulary. We also create an attention mask, which is a binary vector that tells the model which tokens are real, 1, and which are padding, 0. Together, input IDs and attention masks are the numeric inputs into your model. Before we dive into loading our model, let's quickly talk about what BERT is and why we're using it. Bidirectional in BERT means during pre-training, BERT looks at words both to the left and to the right of a masked word, so it really understands context. Encoder means it uses the transformer's encoder blocks to build deep contextual embeddings for each token. BERT has already been trained on huge text corpora, so we don't have to create a model from square one, saving us time. Since BERT already knows a lot about the language, so it needs only a few epochs of fine-tuning to excel on our question sentence inference task. Its bidirectional context means it can better judge whether a sentence truly answers a question compared to older models that read text one way only. By using DistilBERT, a smaller, lightweight, and a faster version of BERT, we keep training time reasonable while still keeping most of BERT's power. We will use the DistilBERT-based uncased checkpoint from Hugging Face because it's distilled. That means about 40% smaller and 60% faster than full BERT, but retains 97% of its performance. Uncased means it's lower cases, all text, simplifying the vocabulary. Once this runs, you have the tokenizer ready. We will create a tokenize function which turns raw text into tensors the model can understand. Let's walk through it. Extract questions and sentences from the dataset and pass it in the tokenizer. Set the max length of the token to 64, since 64 is a good balance of context and speed for QNLI. Set the truncation to true if the combined length is longer than the max length, cut off the excess tokens. To pad every sequence to exactly 64 tokens, set padding to 64, which keeps our batches the same size. And at the end, return PyTorch tensors directly. Apply this function on each segregated data frame to create encodings for each dataset. At the end, a dictionary containing input IDs and annotation mask is returned. These tensors feed straight into our model during training and evaluation. Encoding for a single record should look like this. To feed data into the trainer, we need to wrap our encodings and labels. For that, we create a simple QNLI dataset class by subclassing Torch Dataset. We store the pre-computed encodings and the labels. The getItem function grabs each tensor slice at index and adds a labels field by converting the corresponding pandas label to a PyTorch tensor. The function in the end returns a dictionary with model inputs plus the label that can be used in the model building. We will now initialize the model and tokenizer. Since we have two labels, entailment and non-entailment, we will set the number of labels to 2. We configure our training run with a single object called training arguments. Think of this as a set of dials that control how the trainer behaves. This manages the learning rate, batch sizes, epochs, logging, and checkpointing so you can resume if interrupted. You can play around with these parameters to improve your model performance. What exactly is a checkpoint? It is simply a saved snapshot of your model's weights and optimizer state at a particular training step. Think of it like hitting save in a video game. If anything goes wrong, you can pick up right where you left off. Checkpoints are important for crash recovery. For example, if your process is interrupted due to power loss, preempted cloud instance, you don't have to start over from epoch 1, you just resume from the last checkpoint. Training large models can take hours or days. Checkpoints let you train in multiple sessions without losing progress. By inspecting different checkpoints, you can compare how your model performed at various stages and pick the best one. If you want to try a new learning rate or batch size partway through, you can load a checkpoint and continue with your new settings. We will use the evaluate library to fetch the built-in QNLI evaluation metric, which knows how to compute accuracy. To track how well a model is doing on QNLI, we define a compute metrics function that the trainer calls after each evaluation. Initialize the trainer and train from scratch. In Hugging Face training arguments, you can control checkpoint behavior with parameters like output directory, save total limit, and save steps. Later, you can resume training by passing the folder name back into the trainer. Checkpointing keeps your work safe and your experiments reproducible. To resume from checkpoint, use the following command. After training finishes, evaluate your trained model on the validation set. After loops of training, here's the results. You can save your metrics to a text file if you want to, as well as save your model and tokenize it for later use or inference. Now you have a fine-tuned model ready for deployment or submission. You can use this model for inference on your test data. And that's it. You know now how to set up your environment, load and explore QNLI, tokenize sentence pairs, build a PyTorch dataset, fine-tune a DistilBERT model with checkpointing, evaluate and save the model. So check the description for a GitHub link. Happy modeling!